So the second talk is going to be given by Peter Ney, who is a postdoc at the University of Washington, and he works at the intersection of biotech and computer security, another area where we don't see a lot of papers. So.
All right. All right, thanks for the introduction. This work was done in collaboration with Yoshi Kono and Luis Seze. And I'm going to talk about a paper where we look at emerging security risks to third-party genetic genealogy services. So just to give a little background on direct-to-consumer testing, which is something I think many of you have heard of. So this is the kind of testing that's been popularized by companies like 23andMe or Ancestry DNA. And the idea is that customers will submit a saliva sample through the mail to these testing companies. These companies will physically process the samples in labs to then provide sort of genetic interpretation back to their customers. So this includes things like discussing predispositions to certain medical conditions, predicting ethnicities, as well as trying to find close relatives. But one thing that's important for this talk is that all of the major direct-to-consumer testing companies let users download their raw genetic information. And so this has created a kind of a cottage industry of what I'm calling sort of third-party genetic services that effectively don't do testing themselves, but have users submit this raw genetic data that they have tested at the direct-to-consumer testing companies to these third-party services, which then provide additional add-on analysis. And so these third-party services are going to be the focus of our research. In particular, we focus on a specific type of analysis called genetic genealogy, and services that specialize in this. And so really at a high level, genetic genealogy is basically a set of techniques to try to find relatives using just genetic information. And so you can think of someone like Alice. So Alice would submit her raw genetic information to a genetic genealogy database. This database and service would then try to look for relatives that exist in the database to Alice. And this process of looking for relatives is called relative matching. And so, for example, the genetic genealogy service might say, oh, Bob is Alice's sibling, or Frank is her second cousin, for example. So just to give a little detail on kind of how relative matching works, at least at a kind of a high level. Effectively, when you are closely related to someone, you tend to share large chunks of your chromosomes with your relatives. And the more closely related you are to someone, the more of these kind of large chromosomal chunks you tend to share. And so these shared chunks are referred to as matching segments. And so what relative matching algorithms try to do is sort of is to try to identify people in the database who share long chunks of DNA with you. And then using sort of the known distribution of how many sort of these matching segments different people have, try to make a prediction as to how closely related you are to them. So there has been some work looking at attacks and genetic genealogy services, particularly with identity inference, which will be helpful for discussing some of the attacks we focused on later. And so the idea of identity inference is that you have, say, an anonymous bit of genetic data or an anonymous DNA sample, and your goal is to try to identify the source of that sample. And so the way you do this is you either process this sample or this data and try to effectively forge direct-to-consumer testing data files. Then what you do is the adversary will then upload this unknown genetic data to a genetic genealogy database, which will then return all the relatives of this unknown person. And then lastly, you combine this with family tree information to try to triangulate down to either a small number of people or the actual person that you're looking for. And so this technique has been really revolutionary in law enforcement. And so about 18 months ago, it was used to solve the Golden State Killer case. And so far, hundreds of cold cases have been solved using this approach. And when used with law enforcement, it's referred to as investigative genetic genealogy. But this isn't limited to law enforcement. For example, people have already demonstrated that you can do this with anonymous research data. However, we're interested in kind of two separate but related attacks to identity inference. So the first is whether it's possible for an adversary to upload artificial or otherwise manipulated genetic data to a genetic genealogy service, run standard relative matching queries, and using the results that are returned, try to infer sensitive markers of users in the database. So effectively, think of it as trying to steal data from other users in the database. And the second question is whether it's possible to reliably construct artificial data that looks like a relative of a targeted user in a genetic genealogy service. And so to evaluate these attacks, we wanted to run a study on a service called GEDmatch, which is the kind of most popular of the third-party genetic genealogy services. And as of now, there's over 1.2 million data files uploaded to GEDmatch. And this is the site that's been used extensively by law enforcement. It was used to solve the Golden State Killer case. There's lots of companies that now operate trying to solve crimes using GEDmatch. And really, our goal is to evaluate the feasibility of these two attacks on GEDmatch. So to design the kind of our experiment, what we did was we created two accounts on GEDmatch, one representing a normal user. And under this account, we actually uploaded 5 separate genetic data files designed to look like normal users, and this data was derived from public research data sets. And then the second account, this would represent our adversary, where we would upload artificial data, run relative matching queries, and receive otherwise results and visualizations for these 5 files. So a quick note on ethics. So we were able to upload all these data under GEDmatch's research setting, which effectively limits basically how these files interact with most users in the database. So effectively, these files don't interact and won't appear in relative matching queries for other users. And we made sure to only analyze results between files that we uploaded. So we didn't ever interact or learn about data from real users of the service. The terms of service did allow artificial uploads, and our IRB determined that this research was exempt from review. So, okay, on to our first attack. So one thing that's worth noting is that it's very common, in addition to returning who you're related to give you information for your relatives, exactly how you're related to one another. So showing where in your chromosomes you tend to match people, as well as a number of other visualizations. And so if you dig into it, what GEDmatch shows, and again, this is common in the industry, is effectively 22 visualizations representing each of your 22 non-sex chromosome pairs. And if you dig into these visualizations, the first one kind of represents sort of how how the two files tend to differ from each other kind of at a marker level. And then the second one shows where in the chromosome these matching segments exist. And kind of the key insight is that both of these visualizations actually leak information about the other underlying genetic markers in other files. And we can use this to steal information. And so I'll focus in on this kind of marker visualization first. So we actually had to do a lot of reverse engineering because these algorithms are proprietary on GEDmatch. But all I'm going to go into detail for now is just showing that if you kind of maximize the resolution and zoom in, effectively these visualizations are basically vectors of pixels, where each pixel appears to correspond to a single genetic marker. However, they do appear to be missing many of the markers we would expect. And the color of the pixel gives some information about how, say, 2 potential relatives differ from one another. And so you can learn information from the colors. And so really, the goal now is for an adversary to upload known artificial data, run relative matching queries against a single target, which you can do on GEDmatch, and then using these visualizations, try to actually steal that target's data. So this attack is kind of involved, and I'm not going to be able to go into full details, so this is just kind of a summary. But the idea is using 20 of these artificial files, we upload them and design them in a particular way, and run comparisons against the target to generate basically a large collection of these sort of pixel vector visualizations. Then using an algorithm, which is kind of reminiscent of the mastermind algorithm, we can actually infer which of these pixels correspond to which genetic markers. And this is somewhat similar to some work done by Goodrich back at S&P in 2009 related to DNA sequence alignment. Then, because we know which pixels correspond to which markers, we can combine this with our known malicious files that we uploaded to actually infer the target user's genetic data at these markers. And then lastly, because we were actually missing a lot of markers, we can fill in the gaps using statistical techniques. And so in total, we were able to basically steal over 92% of the genetic markers from our 5 test files with 98% accuracy. Okay. Now, we can also use these sort of matching segments to extract individual markers by using the presence or absence of them as an oracle. However, I won't have time to get into that in any detail, but I just want to point out that this insight was independently discovered at the same time we published this result. Okay, so lastly, I want to talk really quickly about the idea of sort of generating false or artificial relatives. And so, as I mentioned earlier, the amount of DNA sharing determines the relative prediction, right? And so in a parent-child, you'd expect sort of 50% of the DNA to have these matching segments, a first cousin, 12.5%, et cetera. And so, without going into any detail, if you know the genetic markers in any target user, you can reliably generate matching segments against that user. So then it just becomes a matter of, and then of course, once you can generate these matching segments, you can then generate them in the sufficient quantity to basically forge any arbitrary relative degree. So if you think about so the real question is, how do you actually know the markers of some target? Well, in the first approach, we just had one method. We can actually extract them, and we tested that on GEDmatch, and we could basically generate arbitrary relatives. You can also gather DNA surreptitiously, and they're actually interesting, which I'll get into in a second. An adversary might actually be able to forge relatives against themselves, which might be useful to avoid identity inference. And so the way this might work, and this is kind of a sort of a simplified case, but imagine you have someone on the far right, they're that red person over there, and they have a second cousin in GEDmatch, and they're worried that they're going to be identified. What they can do is generate an artificial or false second cousin, spoof the identity of someone else in the family tree, and then what this would happen is someone trying to do identity inference would actually make the incorrect inference, because they would assume that this person, based on the topology of the tree, is actually a relative of that couple at the top, which is in fact false. Now, when you actually learn a little bit about how investigative genetic genealogy is done in practice, it's an open question as to how effective this would be, because it's somewhat of a manual, expert-driven process, and there's a lot of noise, but I think this is something worth considering. We spent a lot of time in the paper kind of thinking about what is it with the way that GEDmatch is designed that kind of contributed to the vulnerabilities that might give insight into the industry at large as to how security issues can manifest in these services. So just kind of at a high level, really, I think the big thing is that there's sort of no authentication or integrity checks of uploads. High-resolution visualizations leak lots of information. The ability to target specific users, you can actually look up users by email address. And then, of course, a lot of these algorithms seem to be vulnerable by design. And so we responsibly disclose these results to GEDmatch, who modified their visualization algorithm to kind of mitigate the most serious of these data extraction attacks. However, I think in the long term, the direct-to-consumer testing industry is going to really have to kind of make changes, especially related to authentication, given that they know that users are routinely testing, downloading files, and uploading them to third-party services to kind of prevent sort of a wide range of attacks via malicious uploads. And so I just want to conclude by talking about kind of a big takeaway about security in the future of genetic genealogy. So I think that these genetic genealogy databases actually have really major implications for genetic privacy. They're used to solve crimes, and very recently, the actual results from these services, including GEDmatch, have been used in court cases. And I think there's a lot of relevance for genetic surveillance as well. So we know, due to some work that was published in Science in 2018, that actually relatively small databases are sufficient to effectively identify any DNA sample. And so once you get to databases around 10 million people, identification is relatively simple, and this is already the size of the larger direct-to-consumer testing companies. And so I really want to encourage the community to think about how we can develop methods that make genetic genealogy sort of more secure by design. And so I'll leave it at that.
there are any questions, please come to the microphone. And we have a question.
Yeah, Josh at BYU Hawaii. So this is intriguing. I live in a state that kind of allows for intentional, legal, racial profiling. Individuals in Hawaii that have a certain amount of quantum, is how they describe it, a certain amount of Hawaiian native ancestry are entitled to certain benefits that others are not. If I'm understanding correctly, you could essentially forge that, falsify that type of information to be able to give yourself that genetic markers to indicate, well, yes, I have this ancestry and gain benefits. Am I understanding that correct?
Yes, so if you were using a service like GEDmatch as the sort of arbiter to make that determination, then yes,
Right.
The answer is that. Yeah, so, but in effect that, it would depend on how that testing is done. So do you know if they're tested at
Yeah,
I
do know that they have allowed for some of these types of things to be able to be indicators of ancestry.
Yeah, I mean, at this point, I mean, like I said, the whole kind of industry is kind of working with these sort of unauthenticated files, right? And so they're completely forgeable and manipulatable. So I think sort of anything regarding that is definitely open.
Wow.
It's definitely possible.
Scary and fascinating. Thanks.
Mm-hmm.
Actually, right?
Yeah.
So what is it that we should be trying to prevent?
Yeah, I think that's a good question. So I think there are ways to imagine doing this in a way that you could have sort of a policy of, say, allowing law enforcement to have access, but preventing some of these attacks. I mean, something as simple as having some sort of authentication where you know these files originated from an actual testing company, right? And that the data that was generated is authentic and, so in this sense couldn't be manipulated and forged, right? So if you had a service like GEDmatch that had some sort of authentication mechanism, then you could imagine that law enforcement could be given special permissions to allow unauthenticated uploads, for example, where normal users couldn't. Now that's a matter of policy, and so then you would debate whether that's something you would want to happen or not, at least from a law enforcement context. But I think there's actually a lot of flexibility.
Reconcile that with the privacy.
Yeah, I mean, well, the two threats that we talked about, I think, yes. If you're talking about identity inference in general, I think that's an open question. I mean, at some level, law enforcement is using identity inference, right? So if you don't like that law enforcement is doing identity inference, then there's really not going to be much of a solution there, right? So, okay.
Well, if there are no further questions, then let's thank the speaker once more.